Hello everyone. This video is the continuation of the previous video where we had concluded our discussion about modification factors. So in that video we had discussed about the three important modification factors, that is based on load, based on size and based on the surface. So now in this video we will discuss the modification factors in detail. First let us start our discussion with the modification factor of size effect. We know that the strength of large members is lower than that of smaller specimens. So it will vary from the size, and this may be due to two reasons. The first one is the larger member will have a larger distribution of weak points than the smaller one, and on average fails at a lower stress. But the larger members have larger surface areas. This is important because the imperfections that can cause fatigue failure are usually at the surface. Increasing the size, especially section thickness I am talking about, results in larger surface area and creation of stresses. These factors leads to increase in the probability of crack initiation. This factor must be kept in mind while designing large size components. Example, the size factors when I speak means based on the diameters only, because the fatigue component example if you are discussing means usually the shaft is the well-known example, always is considered based on the shaft only. These size factors value will be decided, and on what basis this value will be decided. Here in the video the values was not shown, but orally I am explaining here. This size factor will be denoted as k a suffix s is z, and the modification factor based on the diameter, as I said, if the diameter ranges from 0 to 8 mm, then the modification factor value is 0.81, and the diameter value ranging from 8 to 50 mm, the diameter value 8 to 50 mm means then the modification value is 0.85, and if the diameter value is greater than 50 mm, then the modification value is 0.91. So 0.81, 0.86 and 0.91, and the diameter is 0 to 8 mm, 8 to 50 mm and greater than 50 mm. So these values is not available in the data handbook. We supposed to remember while solving the numericals, particularly when modification factors like the indication is mentioned in the question. Moving to the second one, that is surface roughness. Most of them may think why this surface plays a vital role in the fatigue. Of course, even there are many concepts which was completely based on the surface. For example, when we speak about wear, tear, friction, all those things is completely based on the surface roughness only. Almost all fatigue cracks nucleate at the surface of the members. So the condition of the surface roughness and the surface oxidation or the corrosion are very important factor. Experiments have shown that different surface finishes of the same material will show different fatigue strength. Methods which improve the surface finish and those which introduce compressive stresses on the surface will improve the fatigue strength. Smoothly polished specimens have higher fatigue strength. Surface treatments, fatigue crack initiate at free surface treatments can be significant. Plating, thermal or mechanical means to reduce, induce a residual stress. So when I speak about the surface roughness, in it is values can be taken directly from the data handbook, even though the value is not given along with the question. So how to take? So we have two cases, that is based on the tensile, that is axial load like tensile and compressor, and bending load, and similarly based on the torsion. This surface roughness can be calculated if we know the material ultimate strength. And first we will be checking the y-x-axis, where in the x-axis ultimate stress, the given value for the so and so material we will be checking out. In the graph we could able to see many different curves starting from highly polished, polished, normally polished, roughness, again erosion, like different types of surface conditions we could able to see. So in the left side of y direction, with the corresponding ultimate stress value for the corresponding condition, we will be taking down the surface roughness value, that is KSR. Similarly, the right side y axis we will be taking down the shear, that is the torsional loading condition for the surface value. And moving to the next one, effect of temperature. This is cannot be called as a very important modification factor, but still in very rare cases this is also considered. So fatigue test on materials carried out at below room temperature shows that the fatigue stress increases with decreasing temperature. Here you can able to see the stress amplitude versus number of cycles to failure. And here uh, number of cycles starting from 0, 1, like 10, 100, 1000, 10,000, 1 lakh, like that it will keep on varying. You can able to see this, the different stress amplitudes starting from 29 degrees Celsius, 427 degrees Celsius and 76 degrees Celsius based on the temperature conditions. And even the fourth very important property among all the modification factors, that is the metallurgical variable. So this metallurgical variable, here I'll be discussing about the fatigue strength generally increases with increase in UTS, that is ultimate tensile specimens. So the fatigue strength of quenched and tempered steel, that is the tempered martensitic structure, have better fatigue strength. Finer grain size show better fatigue strength than coarser grain size. So non-metallic inclusions either at surface or the subsurface reduces the fatigue strength. So here the metallurgical variables usually for alloys, composites and some other material categories is recommended. And here they have not discussed about loads, but even though it is not shown in the sketch format, I can explain you. Fatigue means usually three different important loads we will be discussing, that is axial load, bending load and torsion. Axial load means tensile or compressive, and for that the value is for that the value is 0.8, and for the bending the value is 0.9, and for the torsion the value is 0.95. Again I'll repeat, for the axial it is 0.85, for the bending it is 0.9 or 0.91, and for the torsion it is 0.95. So these are all the values as usual we need to remember while solving the problems. So temperature it is not playing very important role while solving the problems based on the stress concentration problems, but there are some factors where we will be considering even this temperature also to avoid the failures. And correctly speaking, without considering these modification factors, if we solve the problem, what happens? We may be landing up with the wrong answers that may not be the suitable point or the suitable values to identify the failure conditions. So, these modification factors should be considered very effectively while solving the problems.